In this video, I'll teach you how to use Comsol multiphysics for rotodynamics analysis in the crankshaft. So we start by going to our model wizard, where we'll select our space dimension. So in this work, we'll select a 3D space, work with the 3D space. Then we have to select our physics. Move to structural mechanics, where we go to rotodynamics. So in here, we'll select okay. So we have solid roto, we have beam roto, we have solid roto with hydrodynamic bearing. So that's what we'll be using. Okay. So we move to our steady and select a time dependent steady. Okay, so that brings us to our interface. Have our physics in. Go to our geometry. We want to import it. We go to import. Sorry. Browse. Then we import our geometry. So over here, we'll select we are importing our geometry from a file. So over here, we can see we have several files. We have the geared rotos parameters, and we have single cylinder reciprocating engine. We have turbocharger stability analysis parameters, and we also have this as well. So we'll be using a reciprocating engine. This reciprocating engine roto MD4. That's what we import. So we go ahead to import this, and we have our geometry, as you can see. Now we move to our parameters, where we manually input our parameters. Let's see. 1, 2, and this. Okay. So after inputting, we would add material to our work. And we want to add the structural steel. Okay. So after adding structural steel, we go ahead and we want to add, we go to definitions, functions, and we want to add a ramp. Okay, so the function name label. Let's check the cutoff, the size of the transition zone. Check that to be 0.2. All this to 0.2. And the plots, we have this, as you can see. That's for the ramp in here. The solid rotor. We go to the revolutions per time, and we want to define this as W. W. Good. Let's see the discretization. Displacement should be linear over here. Okay. So once we've made some changes in here, let's go to the linear elastic. Let's add a damping. Okay, so damping will change the mass damping parameter to, let's make it 6 points. We make it 6.04. Make the stiffness dampen to 0.0205. Auto axis. Have the first support and so have the second support. So for the first support, we'll make it 1 and 2. The second support will be at the back. Put 2, 3, 2, and 2, 4, 1. Let's go to the free. The fixed axial rotation. Also, we choose 1 to 8. That's the side we select for our fixed axial rotation. Go to Solidworks and we want to add the thrust bearing. Thrust bearing to, I want to select 11. for our transparent. As you can see, 11 section size is highlighted. And I'll add another thrust bearing, which will also be 131 this side. So as you can see, it shows you where this thrust bearing is. I'll add another part that will be the journal. Okay. Now let me delete this one. I'll add the journal later. So we have the hydrodynamic bearing. Where over here, I'll clear and I'll select particular places. I'll be choosing here. I'll choose here. Go of 30. Then the section 2 as well. Choose the section 2 as well. Right. And I choose here and here. The equation type will be Reynolds. And the bearing type spring. Let's see the sketch. Okay, we have this. We want to make a elliptic and see how it looks like. So make it user defined. There will be an equation in here. So we make a plane and we make the section C. The clearance will be, yeah, C. And the dynamic viscosity, want it to be user defined so that we will put our own dynamic viscosity. Also, our density user defined so that we put in our own density. Okay. We duplicate this, then to make here manual. We clear section 2 as well. Select 50 and 51. 50 and 51. So that's for the hydrodynamic general bearing 2. What we'll do is we duplicate this and also clear selection and select our location. It's 8 and 89. And we'll go ahead and duplicate this again. Add another selection. That will be here. 127 and 126. Go to our solids, to where root is selected as here's solid router. Have the hydrodynamic bearing as well. Maybe we can start building our mesh. In size, let's make it fine. Make it physics controlled. And that builds our mesh quickly. Then we go to time dependent and we want to change the output ranges. Want to make here 1 to the power. Let me change it over here. 183 and 0.25. Okay, so this is what we have in here. Let's get initial value for this. Then we have this. Go to dependent variables. So yeah. We have the pressure we'll change the scaling to 1.5. Time dependent solver. Automatic. Go to the time dependent and let's compute this. Okay. So the error is from the function operator named Rn because we haven't defined what Rn is. So we go to functions and we see that our function name here is Rn. We have to make it Rn so that Comsol we would identify the function. So since we've made this Rn1, can go ahead and compute. So we wait whilst it computes. So this will take some time, but hopefully we'll be able to finish soon so that we can continue the next steps where we plot some of our results and do other more modeling. So as you can see the progress of the work in here. So it depends on the CPU of your machine. If you have a higher RAM, let's say 32 gig, I think this will compute faster. Since we have to actually wait for this work to finish computing so that we can move to the next stage, I think I'll have to skip this and I'll pause and we'll continue when this ends. So now we're done computing. Took about 16 minutes, 28 seconds. So, so as you can see, the stress and the when we start taking the time from going, we see a change in the you see gradually see changes and the stresses across the whole geometry, causing a tilt or the body to deform in a particular way. Okay. So you can see the stresses in the whole body over this period of time. So 0.25 seconds. Go to applied load volumes, as you can see. Shows the intensity of the load volumes at readings. Look at the fluid pressure too as well. See the distribution of the pressure, the fluid pressure in the body over this time. Look this up. Sets okay. How about we take coordinate minus 0.16 to minus 0.055. Then let's do this one. Minus 0.16 minus 0.055, 0.055, 0.154. We have 0. Okay, okay. We have minus 0.28525 minus 0.28525 minus 0.28525 have minus 0.28525. Okay. The 3D cut point. Okay, let's change before that. Let's see. Okay, so this is what we have for the 3D cut point. Go to the fluids and let's add I don't think we can add thinking of adding some objects. Okay. Journal edits. So basically that gives us our results. Okay, so check the Solidworks. So basically it shows the distribution of the fluid pressure, the stresses in this engine rotor. Looking at the time-dependent steady distribution of the stresses and the fluid pressure. Okay.